Okay. Let's see. A couple of things to note about this week in general. One, we do have normal lab this week, so do report in as per normal. This week's lab will be about torque. And so, both balancing meter stick seesaws and also doing the math behind balancing meter stick seesaws. In turn with that, lecture today, we're going to try to close out the last of our rotation concepts. I recorded one video lecture Friday before break about this, but this particular section didn't end up meeting just because of student attendance rates, which is fine, it's the Friday before break. The point is though, if you watched the recording I posted on Friday, then this is all the same material as that. If you didn't watch it, then great, that's what we're covering today. But just to make sure that everyone, as many people as possible, have heard this stuff from me, I am going through it again today. My plan is to try to close out as much of rotation today as we can, and then on Wednesday and Friday move into new chapters about matter and eventually pressure and buoyancy. Does anyone have any questions before we get started today? All right. Now, Wednesday before break, one of the last things we ended on was this image. We've been talking about torque, how in order for something to remain in rotational equilibrium, all the torques acting on it must add up to 0. And we looked at a few seesaw type questions where usually the fulcrum, the point that the object is balancing on top of, the axis of rotation, is usually right under the center of the seesaw. So why is this possible? Like, what's happening here?
The weight distribution.
Yes, the weight distribution is important. This is a real thing that can happen, and it's because of the weight distributions on either side of the fulcrum creating an equal amount of torque. On the left side of the fulcrum, you have a kid sitting, as is true with most seesaws. But what's on the right side balancing out the torque that the kid is creating?
Gravity pulling down on all the weight.
Gravity pulling down on the weight of the seesaw itself. Very good. When the fulcrum is directly underneath a point called the center of mass, or alternatively center of gravity, that's the one spot where you can kind of treat the entire object as if it is a point mass in that location. And the rule is, as long as something's center of mass is supported, it's as if you're supporting the entire object all at once, even if there's pieces hanging off in either direction. As long as the center of mass, center of gravity is supported, the whole item is supported. So when the fulcrum is on the center of mass of the seesaw, or under the center of mass of the seesaw, the weight of the seesaw doesn't actually affect anything, because if the fulcrum is supporting that weight can't generate any torque. Additionally, torque formula helps with this. The weight of the meter stick can't generate any torque if that weight is at a radius of 0 from the fulcrum. So if the center of mass of the meter stick is right here, and the fulcrum is directly under that point, 1, the center of mass is supported, so the whole meter stick is supported, and 2, the radius between the weight of the meter stick and the fulcrum is 0, so that weight can't generate any torque. The second you move the fulcrum away from that spot, suddenly the weight of the meter stick is at a radius away from the fulcrum, and the center of mass is no longer supported, so by itself the stick would start rotating around the new fulcrum. And that is why in the previous image there had to be a kid sitting here to keep it level. So an object's, the position of something's center of mass is important to understand if you're trying to figure out if it's going to rotate or not. If you want something to remain stable, you have to support its center of mass. So the rule for whether or not something's going to fall over depends on if its center of mass is being supported. Where something's center of mass, center of gravity, I use them as synonyms, apologies. Where something's center of gravity is depends on the object, both its shape and what it is made of. Usually if something is a standard enough geometric shape and it's made of one uniform material, its center of mass should be somewhere in the physical center of the object. So again, with the wood of the seesaw, as long as it's a standard geometric shape, in this case this is just a really big boxy shape, or really long box. And as long as it's made out of one material, which it is, it's all just the same type of wood, its center of mass should be somewhere in its center. Same as this oil drum picture here. That's just a cylinder, which is a geometric shape, and the walls are all made out of the same metal, probably. I don't have an oil drum, but I do have a metal water bottle, so I'm going to use this instead. If it's a standard geometric shape and it's made out of mostly all one material, its center of mass should be dead center. So if you want to keep it from falling over, you have to make sure that that center of mass is directly being supported by something underneath it. And it'll remain upright, it won't start rotating, as long as that center of mass is being vertically supported. I can tilt this thing slightly and it'll still fall back onto my hand, as long as I don't tilt it so far that the center of mass goes over the edge of my hand. As long as just consider my finger, the spot where I point my finger to be the center of mass. As long as that spot doesn't drift over the edge of my hand, it'll just fall back onto my palm. But if that spot goes over the edge, it falls. And that's because when it's that far away from my palm, the weight is now at a radius away from an axis of rotation. It makes torque and it rotates away. So to keep something from spinning, and most things that fall over actually rotate in order to do that. Like for this thing to fall off of my hand, it does have to rotate away. If you want to keep something from rotating and falling, you have to make sure that its center of gravity is being supported in some way, shape, or form. And it will fall over, rotate, if that center of mass is not being supported, if its own weight is allowed to start generating torque. Architects have to be conscious of this, because if they make their building too top heavy, strong enough breeze can cause it to tilt far enough that its center of mass is no longer being supported and it falls over. So most buildings tend to, on purpose, be heavier on the lower floors and lighter on the upper floors to try to prevent that from happening. Especially if you live in an earthquake-rich region. We've developed a lot of tips and tricks to try to keep earthquakes from destroying skyscrapers. Questions so far? All right. Now, kind of jumping off from that point, where something's center of mass is does kind of depend on its mass distribution, which can start getting complicated if you're looking at a non-standard shape or if the object is made out of more than one type of material. Skyscrapers, as I kind of hinted at a second ago, they're sometimes not geometric shapes if you're getting artistic with it. And they're also made out of more than one type of material. So architects have to be very careful to put the heaviest materials on the bottom, and usually to try to make it physically some kind of a shape that is bigger on the bottom than on the top. To kind of demonstrate a more down-to-earth place, you might have seen something like this. I'm torn on what exactly to call this shape. Some of you might recognize it as a boxing bag, something you punch and then it would spring back but then come back up so that you can punch it again. But additionally, the same principle applies to a toy, children's toy that you might have heard of called a Weeble. A Weeble wobbles and it doesn't fall down. How old do I sound right now? The physics behind this, whichever version you are choosing to envision right now, this object is almost a standard geometric shape. You could think of it as, a cone. But the main thing about this is what it's made of. The objects like this tend to have metal in the very bottom, but lighter materials up top. If you were to use the punching bag example, a punching bag using this principle would have metal weights in the bottom, and the top part would probably be made out of something that is, punchable, like fabric or foam. And when you punch it, since all the weight is at the bottom of the object, its center of mass has shifted down there. The center of mass always follows the mass of the object based on the mass distribution. So if this part is metal and this part is like styrofoam, all the weight is centered down here, and that lowers the center of mass. When the center of mass is physically lower, it's harder to knock something down because that center of mass doesn't actually move all that much away from where it was. Whereas if your center of mass is very far away from the point that it's rotating around, then that's a bigger rotational radius and it's more likely to generate enough torque to completely fall over. The lower the center of mass is, the more stable things tend to be because it's close, the mass itself is closer to the axis of rotation, doesn't generate as much torque, doesn't take as much torque to then put itself back to normal. So that is why something like this doesn't usually fall over, even if you punch it really hard. Same principle applies to a different children's toy. Is anyone familiar with the birds that you can balance on your fingertip? When I was growing up, the most common place I would tend to see these was at like the toy counter at like Chuck E. Cheese or something like that. You get 5 tickets and you get a bird that doesn't fall off your fingertip. It's okay if I sound very old right now. This toy and similar toys, they aren't always birds, uses a similar type of a principle, but rather than making the center of mass lower, they put weights in the tips of the wings and in the beak to shift the center of mass away from the body and physically underneath its beak. And so therefore, as long as your finger is supporting the beak, you're supporting the whole thing and it doesn't fall off your finger. I checked the closet time and time again, and we don't have one of those, unfortunately. Although, I guess the weight right on something like this. This is the same basic principle. Just consider this part to be the hollow plastic body of the bird, and this part to be the beak that has a physical weight in it. Now, objects do like rotating around their centers of mass, and so if you're doing any work with rotation, it's worth trying to note where that point is. Objects like spinning around that point. You want to make sure that point is supported if you don't want something to spin and fall. A couple places where this sort of thing shows up is actually in tightrope walking, interestingly. Have any of you ever watched something like this, either on TV or at a circus, and wonder what's the point of the pole? Is that a question any of you have ever asked? It's okay if not. The reason that they use that particular object is actually to manipulate their center of mass to make this task easier to perform. If you are trying to do something like this, you want your center of mass to be, first of all, you want more mass in your body, actually, because the more mass you have, the harder it is to make you spin. And technically, to fall off of this thing, you have to rotate off of it. Because as long as your center of mass is being supported by the tightrope can actually hold you up. The issue is if you spin and your center of mass is no longer over the rope. So the reason for the pole is, one, it adds more mass to their body, and the more mass you have, the harder it is to make you spin. Kind of like how the more mass you have, the harder it is to make you move, period. So physically, the more matter they have that they're holding onto, the harder it is to make them spin. But furthermore, these poles they're never usually just solid wood. They usually have metal weights in the ends, and that's why they tend to dip if you're ever watching this at the circus. They tend to be very long and they tend to dip so that the ends are hanging very low. Not only does that increase the total mass, that also lowers their center of mass, because if the ends are metal and they're hanging down, that takes the center of mass of the person and makes it lower. Most humans have their center of mass somewhere in their torso. Exactly where depends, because humans are not standard geometric shapes. But the lower your center of mass is, the harder you are to knock over, because the lower it is, the easier it is to get support from whatever you're standing on. So the pole makes it harder for them to spin off of the tightrope, and therefore they can stay on it longer. But this is not the only place where this sort of thing does appear, which I haven't met many tightrope walkers, so it's good to know that this has other applications, in my opinion. Knowing where something's center of mass is useful if you are trying to make it spin or make it not spin, because objects do like spinning around their center of mass. I'm not going to throw the whole 2 meter stick. Instead, I'm just going to throw this thing. Even though there's a piece of it missing, you can still consider it to be a standard geometric shape made of all one material. So right now, its center of mass should be in its center. So if I make it start spinning spontaneously, it's going to, sorry about that, spin around its center. But if you can manipulate its center of mass, you can manipulate the spot that it's spinning around. I will now manipulate its center of mass by adding some weight to one end of it. This, frankly, if I'm being honest, this is probably heavier than this. Yeah, this is more weight than the entirety of this ruler is. And I am now going to clamp it onto the far end of this object. Kind of like with what the tightrope walker's pole is doing, this is going to shift the center of mass of the object. No longer is its mass concentrated here, since now there's a bunch of metal on one side. Now its center of mass is concentrated somewhere up here. Literally, that is now where its center of mass is. And that is now the spot that it kind of most naturally wants to spin around. Did you see it? Not spinning around its very center anymore. Ow! Why do I throw things when I can't catch them? Fun fact related to this, this affects most tools that humans have invented, if I'm being honest, because most tools make some amount of use of torque or rotation. If you are using a tool where the center of mass is further away from your hand, it's typically harder to spin, and that includes spin or swing, and that includes hammers and axes. If the center of mass is closer to where your hand goes, which honestly the best historical example I can come up with for that is a sword, whose centers of mass are typically somewhere near the handle, that tends to be a bit easier to swing around, because if you're moving the center of mass, you're better able to manipulate the item as a whole. Now the counterpoint to that is if the center of mass is here, you're not doing as much damage by hitting something with the end of it, because hammers deal damage by physically hitting something with the heavy part, and that's why swords need edges to be able to do anything of use. If you want to try to feel that yourself, take this and just move the clamp around and kind of see how it feels one way or the other. Feel free to do that. I'm just going to leave it on the front table. Understanding center of mass benefits you if you are trying to make something spin or keep it from spinning, which, again, architects want to keep things from spinning. People who design tools and wheels want things to spin, so they do have to understand this sort of stuff. But it turns out it's not just the location of the center of mass that affects rotation. Before I switch gears, any questions? All right. It's not just the center of mass that affects how something spins. That is part of it. But how something spins also depends on what axis you choose to make the item spin through. You do have to know its mass, and you do have to know where its center of mass is, because that tends to be the spot that it wants to spin around. For example, I'm not going to throw a plank of wood, instead I'm going to throw this thing into the air. This is the same basic shape. It's just a notebook from the bookstore. Or merch store, I guess. This is basically one geometric shape, same shape as a plank of wood, and it's made of the same-ish material. You know, the cardboard and the paper are all just carbon. And so its center of mass should be dead center, and that is the spot that it likes to spin around. But the axis, there's 3 different axes going through that center of mass. If you remember that we live in 3-dimensional space, you can have something spinning through the x-axis, the y-axis, or the z-axis. And it turns out, not only does the object's mass and the location of its center of mass affects how easy it is to make something spin, the axis you choose affects how easy it is to make something spin. To try to demonstrate this, I'm going to take this notebook and I'm going to throw it 3 different times into the air, using each of these different axes. And I want you to just notice how fast it's spinning each of the ways that I throw it. Because if it's easier to make it spin through that axis, it should spin faster. And if it's harder to make it spin through that axis, it should spin slower. Does that premise sound all right before I start throwing the book? Okay. So I'm just going to follow along in the order that I drew these. The first way I'm going to spin this is through the y-axis, so kind of like if you were tossing a pizza. Just kind of consider this your baseline for velocity. Good notion of how quick that was spinning. All right. Now instead of the y-axis, I'm going to spin through the, let's call that the z-axis, because it's pointing out of the board. So now I'm going to do it like this. And just try to notice faster or slower rotation than the first way. Ow. More or less rotation? More. It's not a trick. It is literally spinning faster. I'll try to do them back to back. First Z, then, no wait, first Y, sorry. And then Z. This object inherently is easier to spin through this axis, and that has to do with its mass distribution. The distance from this axis to this edge of the book is smaller than the distance from this axis to this edge of the book. And that means that through this axis, more of the mass is further away, and it takes more torque to get it to spin. Whereas through this axis, more of the book is closer, R is smaller, so it's easier to make it spin that way. There's a third axis though. I'm going to do it through the X this time. I want you to really pay attention to this one. So I'll do them all. Why am I like this? I'll do them all back to back again. First is Y, then is Z, and now watch X. Is that faster or slower than at least the fastest one? Slower than the fastest one, so it's not the fastest axis, which makes sense because this edge of the book is, again, still further away from this axis than this edge is to that one. But there's something especially weird when I do it this way. Do you notice something odd happening when I do it like this? You might have noticed it if you ever throw your phone in the air, because usually when you flip your cell phone, it's the same basic shape, and you tend to flip it about that same axis. It does kind of a backflip. Like kind of on the way up, not only does it spin like this, but once or twice it might do this. Like spin still the same way, but also like this at the same time, once or twice. Again, you might notice that if you've ever flipped your phone around much. Just be very careful if you do that. That is a thing that happens, and that is meant to be evidence of the fact that the book doesn't like spinning this way, because it literally will reject that axis and temporarily choose a different one. Objects of this shape don't like this axis, and so they do the backflip to reject it, at least temporarily. If you don't believe me that it's doing the backflip, I'm going to try to prove it to you. The way that I'm currently holding the book, the text on the cover is right side up facing you guys. And if I throw it like this, there's only two directions that text should ever point. Either right side up facing you, or upside down facing the board. You agree that those are the only two options if I start here and throw it like this? Okay. I might need to do this a couple of times, but I'm going to throw it and we're going to see if it spontaneously does something different when it lands. I suppose I have to catch it though. Aha! It's upside down facing you. That was not one of the two options. That's because it did the backflip. Again, if you don't believe me, try it. You can try it yourself with my notebook or your phone if you feel brave. But this happens because the axis of rotation affects how easy it is to make the thing spin. This axis the book doesn't like, and it does that backflip to fight against that axis, to try to temporarily choose a better one. In physics, we summarize this concept with the name moment of inertia, also alternatively called rotational inertia. As we've been talking about rotation stuff, I've been comparing it back to linear stuff. You know, linear displacement, velocity, and acceleration is the counterpart of angular displacement, velocity, and acceleration. Force is the counterpart to torque. Linear force moves in straight lines. Torque makes things move in circles. This rotational inertia is the angular counterpart to mass itself. Normal mass, m, is a measurement of normal classical inertia. And normal classical inertia, per Newton's first law, says that objects will resist changes in their motion based on their mass, based on their inertia. The more mass something has, the more it will resist your attempts to change its motion. That's why the more mass something has, the harder it is to get it moving, and also the harder it is to stop. Rotational inertia tells us that the more rotational inertia something has, the harder it is to change its spinning. The more rotational inertia something has, the harder it is to get it spinning, and also the harder it is to stop it from spinning. Whereas the less rotational inertia something has, the easier it is to make it spin and also to stop it. This is again just the counterpart to normal mass, normal inertia, and it does tell you how much something's going to resist changes in its spin. And the same object can have different rotational inertia for each rotational axis. That was the point of me throwing the book. Each axis changes its moment of inertia, angular inertia. They're synonyms again in my brain. I tend to flip-flop between synonyms. Each different axis changes the rotational inertia because in each axis, the mass of the book is at a different distance away from that axis. And so something's shape and the axis you choose to spin it through affects how easy it is to make that particular thing rotate. How does that concept feel for right now? Okay. Now, information about the variable that is rotational inertia. It's uppercase I in any formula that requires it. So this is supposed to be an I right there, uppercase English I. It's a scalar, like how normal mass is a scalar. And it has its own very weird unit that I don't especially care to say, that I don't care for. Kilograms times meters squared. It's a very odd unit. And every different shape has a different moment of inertia depending on its shape, its mass configuration, and what axis you're trying to make it rotate through. To try to illustrate this, I'm going to tab to a different slide now. Several textbooks and formula sheets will have charts showing the different ways to calculate moment of inertia for different shapes. This is one sample chart from an old textbook that I used to use. You guys have a similar chart on your formula sheet, if these are ever required, so it's just the back page. And we're just going to focus on these 4 things up here for a second, just to kind of illustrate how the shape and the mass distribution affects the rotation. These 4 shapes up here, we've got a hollow cylinder, a solid cylinder, a solid sphere, and a hollow sphere. And each of these have very slightly different formulas. If they're hard to read on the board, I've got them rewritten over here. So these are the formulas for each shape. You would not have to memorize any of these. They are on the formula sheet if you ever need them. I would always tell you which shape to look up. They are all very similar formulas. They all have mass times radius squared. And what this should tell us is the more mass something has, the harder it is to get it spinning. Same as how the more mass something has, the harder it is to push it in a straight line as well. But furthermore, the size of the item, the radius in the case of these round shapes, also affects rotational inertia, because the bigger something is, the further more of its mass is away from the center axis that's going to spin around. The smaller a shape something is, even if a very high mass object can still be very small if it's like a very high density material, and the smaller it is, the physically easier it is to get that thing spinning than the same mass but bigger. And that's because the bigger something is, the bigger its radius is, the further its mass is away from that center axis, and the more torque it needs to get it spinning. As it relates to all these different shapes, kind of comparing real quick, a solid cylinder to a hollow cylinder, the solid cylinder has a formula of 1/2 times its mass times its radius squared, whereas the hollow one loses the 1/2 out front. And so 2 cylinders that have the same mass and the same radius have different moments of inertia if one of them's hollow. The hollow one is ironically harder to make spin as long as the masses are the same. And that's because for the hollow one, all of its mass is now further away from that center axis. One of the houses I lived in growing up was near a construction site, and so me and the neighbor kids would often go look at all of the buildings that were being built, and occasionally they had those big concrete pipes that they put underground for plumbing. No matter how hard we kicked any of those, we couldn't get them spinning. And that's because if the cylinder is hollow, all of its mass is further away from the edge, from the middle. Whereas if it's solid, it's all distributed a bit more evenly. There's more of it closer to the center, and so it is easier to make it spin if the masses are the same. That's kind of the weird part, because for these 2 masses to be the same, this would have to be made out of a much denser material. It'd be like comparing plastic to metal in order for the masses to be the same. But if they are the same, this is still the harder shape to get spinning, because that would put all of the mass further away. Same basic principle with these spheres as well. The solid sphere has a 2/5 out front, whereas the hollow one has a 2/3. So if their masses and radii are the same, the hollow one has a bigger moment of inertia, therefore it's harder to get it spinning. So the shape, its mass orientation, affects how easy it is to get it spinning. Additionally, never mind, I lost my train of thought. Questions so far? All right. I've only got one more thing I want to talk about today. This is the last rotational concept. I just kind of want to get through it so we can move on to something else next time. This is the last one. I've been talking again about linear versus angular counterparts. Momentum is another one of those linear motion things that has an angular counterpart. Linear momentum tells us that an object that is currently moving in a straight line wants to continue moving in a straight line, and it doesn't want to change directions, and the amount of momentum will tell you how hard that object is to stop. The same can be said of a spinning object. If something is spinning, it has angular momentum instead of linear momentum. And an object's angular momentum compels it to keep moving at the same rate of rotation in the exact same axis. So if a wheel's spinning clockwise, it wants to keep spinning clockwise and will never spontaneously start spinning counterclockwise by itself. Does that make sense? Okay. Now, where this gets really weird is when you realize that rotational vectors, and in this case angular momentum, doesn't only care about clockwise versus counterclockwise. Angular vectors also care about which axis they are currently spinning. Because I can make something spin clockwise or counterclockwise around the y-axis, or around the x-axis, or around the z-axis. And something that's spinning not only does not want to change from clockwise to counterclockwise spontaneously, they also don't want to change which axis they're spinning around. So if something is spinning clockwise around the y-axis, it wants to keep spinning clockwise around the y-axis, and it doesn't want to change. This is a gyroscope, which is basically just a very specific type of top. And if I can get this to work right, I'm going to try to show what I mean. It didn't work right. All right, take two. There we go. This gyroscope is currently spinning clockwise around the y-axis, and it does not want to change either of those two details. If I try to make it rotate about a different axis, if I try to tilt it away from the y, it resists and fights me. It didn't immediately fall over. It tries to stay upright. And that's why all tops, okay, this is a bad gyroscope. It was not illustrating the point very well. So instead, I'm going to use this. This is, once again, the disembodied bike tire of science. Normally, if I just try to hold this thing by the rope, it's just going to fall down, right? However, if I make this thing start spinning, from your position, I would say this is spinning clockwise around the z-axis. Once it's spinning clockwise around the z-axis, it does not want to change either of those two details. And so if I hold it up by the rope again, it'll actually fight gravity and not fall over. This is the gyroscopic effect. This is why tops stay upright as long as they keep spinning. If you ever get a top going and you flick it, it might bounce around like a literal Beyblade, but it'll stay upright and balanced until it runs out of steam and stops spinning. Anything that is gyroscopically stable has something like this spinning around inside of it in order to keep it upright. This is also why bikes stay upright as long as they're moving, because the wheels don't want to turn away from whatever axis they're currently spinning on, which is why if you ever learned how to ride a bike, you were probably advised to never do this with your handlebars. Sound familiar? Because if you are riding and you do this all of a sudden, things tend to go pretty poorly in my experience. Usually if you're riding a bike and you want to turn, you have to lean into it gently without doing this. And that's again the gyroscopic effect. The wheel does not want to suddenly change axes, and so it'll literally fight me to try to prevent that from happening. I'm not making this wobble on purpose right now. I'm just trying to spin it slowly, and it is resisting me because its angular momentum doesn't want it to change how it spins. If you ever want to try this yourself, either trying to make it move or hanging it like a gyroscope, feel free to try that as well. Something that's spinning wants to keep spinning, same direction and around the same axis, and will not spontaneously change. That's what this part tells us. This is the angular momentum formula, and it's really just the same as the linear momentum formula. It's technically still momentum equals mass times velocity. It's just L is angular momentum. No one has ever told me why we use L for that, unfortunately. Angular momentum equals rotational inertia instead of linear mass times rotational velocity instead of linear velocity. So it still works the same way, like how all the rotational stuff borrows the same logic as the linear stuff. If you can get some object rotating, it'll have some amount of angular momentum compelling it to keep rotating in exactly the same orientation. And that angular momentum is conserved from start to finish of some process. So this is conservation of momentum again, just angular momentum instead of linear momentum, L instead of rho. Now, there are scenarios that can, let me rewind actually, get a sip of water. When we're looking at linear momentum, we would tend to use this formula describing a collision, a scenario where there's a certain amount of momentum in a situation, and that amount remains constant afterwards, even if it's distributed between two objects differently. You can do that with rotational momentum, but rotational collisions are kind of weird. The best rotational collision I can think of is like a gear spinning on its own before another gear spontaneously slots into it. Now they're both sharing the angular momentum. That is a thing, but that's not the kind of thing I'm going to ask you to do. Instead, this is the type of conservation of angular momentum scenario I would expect you to be able to recognize. In this situation, which I will replicate shortly, we have a person sitting in a chair, holding two weights, and as a result of them sitting in this way, they have a specific moment of inertia, rotational inertia. And that is, again, the I in this formula. And that rotational inertia depends not only on their mass, but also on the radius of that mass from their rotational axis. So that is why in this first picture, this person is holding these two weights out to the side. That is increasing the distance of that mass from their center. And so in this first picture, they have a certain very large moment of inertia. They've increased their moment of inertia by increasing their mass and increasing the radius at which that mass exists. So in the first picture, they have a very big moment of inertia. And they then begin spinning in place in this chair. So rotating about the vertical axis. Once they're spinning, they have a certain amount of angular momentum, and that's the momentum that tells them to keep spinning in the same direction around the same axis. The weird thing about moment of inertia, rotational inertia, the I, is that unlike normal mass, which doesn't really spontaneously change, moment of inertia can change because it's a function of radius. And an interesting thing about having limbs is you can choose where they are. So if I'm saying I because I'm about to physically do this. If I am in this scenario and I choose to pull in my arms, that has decreased my radius. And if I decrease my own radius, it doesn't really matter which shape I am. All these formulas tell me that if radius gets smaller, moment of inertia gets smaller. So if I am in this scenario and I pull my limbs in, I am going to decrease my moment of inertia because I have now pulled the mass closer to the axis of rotation. That means I will now be easier to spin. Now, what conservation of angular momentum says is, even if I reduce my own moment of inertia, that is not going to change my total angular momentum. Instead, if I cut my moment of inertia in half, my angular speed will double to make sure I have the same amount of angular momentum still. The angular momentum is constant from start to finish. So if I cut my moment of inertia in half, my angular velocity has to double so that I have the same amount of angular momentum. I will now demonstrate. Here I have a rotating stool and two weights, one in either hand. I am going to sit here. I'm going to hold the two weights out here. This again is going to increase my moment of inertia because more mass and a bigger radius. And I'm going to spin in place. Notice how quickly I am spinning. And then I'm going to pull in my limbs and reduce my moment of inertia. In 3, 2, 1. And back. My head. Please tell me that was very obvious and I don't have to do it again.
I think I need to see one more time.
Dang it! Do it the other way.
I'm kidding, but
I know you're just messing with me. Okay. So that is what conservation of angular momentum means. Even if you change one of those two things that make up angular momentum, the other has to also change to compensate. If you cut rotational inertia in half, you will double angular velocity, and vice versa. The sorts of places where you could expect to see this sort of thing in real life include figure skating. You ever notice how figure skaters will often have their limbs all splayed out before they enter a turn, and then they'll pull them all in and start spinning in place super fast, and then they'll throw their limbs back out before they exit the turn and go on about their business? Same thing. They pull in their limbs, reduce their moment of inertia, increase angular velocity to compensate. But, related phenomenon, this affects dizziness in humans. I'm not a biologist, but I know that dizziness is caused by a combination of your brain fluid spinning and your inner ear fluid spinning. Because humans are not one solid object. We're a bunch of different objects attached together and filled with fluid. So if you spin on that chair, your fluids will start spinning too. And once your solids stop, that does not necessarily stop the fluids, because they have their own angular momentum telling them to keep spinning. And so dizziness is caused by your brain fluid and your ear fluid still spinning, even though your brain isn't spinning anymore with them. And that's kind of why it feels like your whole world is still rotating with them. So if you are ever dizzy, the easiest way to stop it is to actually spin once or twice in the opposite direction and try to take the momentum away from those fluids. Sound good? All right, so that was a lot of rotation info today. I've got one sample question that we'll do next time. I'm not gonna hold you up now. So Wednesday, we'll do just the tiniest bit of math to make sure all this makes sense to you. And then we'll move on to some new concepts like matter and pressure. Is there any questions for right now? All right, in that case, this is a wonderful day. Let me know if you need anything. And report to lab as normal this week.